This video gives a number of worked examples based on state space analysis. The prime role of this video is to present worked examples so students can practice. What we would advise is you first look at the problems and try them by yourself before you look at the solutions, and do use MATLAB to test your answers. Now, a reminder of a key result that we're going to use: if you have a transfer function of the type given here, then it's known that a state space model takes the form given here, and that's covered in the earlier videos. First question then. Find a state space model in control canonical form, and here you're given a differential equation. Now you remember the main trick is first to identify a set of states so that you can create a number of first order differential equations. So what I'm going to do is I'm going to say dx dt equals x1, d2x dt squared equals x2, which also happens to be dx1 dt, d3x dt cubed equals x3, which also happens to be dx2 dt, and finally d4x dt to the 4 equals x4, which also happens to equal dx3 dt. So you'll notice I've introduced a large number of new first order differential equations, and if you've not spotted them, we've got this one here, dx dt equals x1, this one here, x2 equals dx1 dt, this one here, x3 equals dx2 dt, and x4 equals dx3 dt. Now I can also substitute these new variables into my original ODE, but I'm going to do something slightly different. First of all, I'm going to solve this ODE just for u. So I'm going to write u equals, now if I put d5x dt to the 5, you'll find that this is the same as dx4 dt because of the definition of x4. And then I'm going to get plus 2x4 minus 2x2 plus 3x1 plus 4x. So you'll notice how I've transformed the original ODE, but with a subtle variation that I'm solving for an input just of u rather than the u that I've been given. So the next step is say, okay, how many ODEs have I now got? I've got 1, 2, 3, 4 and 5, and so I'm going to take those 5 and I'm going to build myself the corresponding state space model. So here we go. I'm going to write my vector x dot, x1 dot, x2 dot, x3 dot, x4 dot equals, and this is going to be multiplying a vector on the right hand side, which is clearly x, x1, x2, x3 and x4, and I've also got something times u. So x dot was given by x1, so I'm going to get 0, 1, 0, 0, 0. x1 dot was given by x2, so I get 0, 0, 1, 0, 0. x2 dot was given by x3, so we get this, and x3 dot was x4. So that's the top part, and then the next part was the bit that had all the coefficients in. So you remember that x4 dot had, let's just go back and see, so we can see it. Oh, we've lost it. So it's got coefficients of 2, minus 2, 3 and 4. So here we go. So we've got 2x4, and it becomes a minus because it's changed to the other side. We've got no x3, we've got 2x2, we've got 3x1 and 4x. So there's our equation. Now the u, we had a 1, a 0, 0, 0, 0, and 1. So there's our A and B matrices, which solve this differential equation with the right hand side of u. So what we've done is we've solved how x of t depends on u, but the input was not u, but instead it was minus 3u plus 7 du dt. Okay, so what we're going to have to do is look at the relationship between the answers. So y of t is going to be minus 3x plus 7 dx dt. So we've solved for x in terms of u, but the actual input is minus 3u plus 7 du dt, so y is going to be minus 3x plus 7 dx dt. And therefore we're going to get y equals minus 3, 7, 0, 0, 0 into this vector x. And that's the end of question 1. Question 2 then. Find a state space model in control canonical form, and now we've got the system as a transfer function, but we're going to use a similar trick to before. What I'm going to do is first of all solve for x of s equals 1 over s to the 4 plus s cubed plus s into u of s, and after that I will write y of s equals s cubed plus 4s minus 1 into x. So that's how I'm going to solve this particular problem. So what we've got then is s to the 4 plus s cubed plus s into x of s equals u of s, or if I write these as differential equations, I'm going to have x 4 dots plus x 3 dots plus x dot equals u. So what states do I need here? Well, I'm going to introduce a number of new states then. So I'm going to write x1 equals x dot, x2 equals x1 dot, x3 equals x2 dot. So I've got 3 new states here. And then finally you'll find that implicit in this is therefore the fourth derivative of x is going to be the first derivative of x3. The third derivative of x is going to be just x3, and the first derivative of x is going to be x1. So I've now replaced my original equation by a first order differential equation. So now I've got 4 equations. I've got my original equation here in terms of the new states, and I've got equations defining my new states. So all I've got to do is combine these and put them into the matrix. Now I've put 0 there, that was careless, that clearly should be u. So I've got to take these 4 equations and build them into a state space model. So here we go then. So I'll define first of all my vector w3, w2, w1 and w. And what have we got here? We're going to have w3 was, oh, those are dots. Let's put the dots on. So w3 dot, how did that depend on w3, w2, w1 and w? So we had minus 1 w3 and we had 1 w1 and nothing else. w2 dot was w3, so we get 1, 0, 0. w1 dot was w2, so we get 0, 1, 0, 0. And w dot was w1, so we get 0, 0, 1, 0. So there's our A matrix. And if we look at the B matrix, we had something like this. So there's my A and B matrix. And now what I need to do is remind myself of the output equation. So we had y of s equals s squared plus 4s minus 1 into w of s, or in other words, w double dot plus 4w, oh sorry, that should be an s cubed, so it's w3 dot plus 4w dot minus w. And if we write that in terms of our new states, then that is going to be w3 plus 4w1 minus w, and therefore y is going to be 1w3, no w2, 4w1 and minus 1, and that into my state, whatever I want to call this state, call it x. So there is my C matrix. Okay, this question says find the state space model in diagonal canonical form. So there's the model, and you remember, to do diagonal canonical form, the first thing we've got to do is partial fractions. So I'm going to write the partial fractions for this system. We're going to get 4s plus 1 over s cubed plus, that should be s to the 7s squared plus 14s plus 8 equals, and it's going to come out like this: a over s plus 4 plus b over s plus 2 plus c over s plus 1, because you can see if you factorize the denominator that it's got roots at -4, -2 and -1. So now what we do is we find separate models for each of these partial fraction terms. So I can write x1 dot equals minus 4x1 plus u, and that will map the s plus 4. I can write x2 dot equals minus 2x2 plus u, and x3 dot equals minus x3 plus u. And you'll notice that when I've done these equations here, for now I've ignored the numerator on these terms. I've ignored the a, b and c, and I've just taken them to be 1. So now I can do a state space model for these 4 equations. So what I'll get is x1 dot, x2 dot, x3 dot equals, and we'll get minus 4, 0, 0, 0 minus 2, 0, 0, 0 minus 1, and that will be into x1, x2, x3, and they all just had an input of u, so I get plus 1, 1, 1 into u. And the final step is to recognize what the output is. Well, the output y is going to be a x1 plus b x2 plus c x3, and therefore your output matrix is going to be a, b and c, obviously into the vector x. And I'm not going to bother solving for a, b and c here, as that's a partial fraction problem and you can do it by yourself. Okay, next one. Find a state space model in control canonical form. So you'll notice the difference here is we've now got a discrete model rather than a continuous model, but otherwise the same sort of concepts as before arrive. First thing we're going to do is ignore the numerator terms and treat it like a 1. So what I've got is z to the 4 plus 1.2 z cubed minus 0.6 z squared plus 0.2 into x equals u. So that's what I'm going to do first as my first equation, and now I'm going to define some new states. I'm going to let x1 equal x, I'm going to let x2 equal zx, x3 equal zx2, and x4 equal zx3. And Also, I'm now going to use these definitions of my new states, and I'm going to plug them in to the corresponding equation I get from here. So z to the 4 is the same as writing zx4. So I've got zx4 plus 1.2 x4 minus 0.6 x3 plus 0.2 x1 equals u. So I've rewritten the equation in a form which now is first order. You'll see I've just got a single z in the equation, and I've got a single z in all the other equations. So now I can write my discrete transform like this. I'll put my z outside. So you'll see I've got z, and then I've got x4, x3, x2, x1. And what's that going to be equal to? So let's draw the matrix, and we'll put our x4 and so on down again. So x4, x3, x2, x1. So the top line is taken from the generic equation. So you're going to have minus 1.2 plus 0.6, 0, and minus 0.2. So I've squeezed that in a bit too much. x3, or zx3, is x4. So you get 1, 0, 0, 0. x2 is zx1. So you get 0, 1, 0, 0. And I've missed something here. And zx1 is x2. So I get 0, 0, 1, 0. There we go. And I add my input, and you see I've got 1, 0, 0, 0 into U. So that's my A and B matrix. And now I need to ask myself, what is the output? Well, the output Y is given by Z squared minus Z plus 0.3 times the x that I got from my original problem, which was x. So now I need to go to a new page, and you'll remember that z squared x was given. So I'll rewrite this more carefully. So what we've got is y equals z squared x1 minus z x1 plus 0.3 x1, which is the same as x3 minus x2 plus 0.3 x1, and therefore y equals 0, 1, minus 1, 0.3 into the overall vector of x. Next question then. Find a transfer function equivalent to the following state space model. So there's the model, and you remember we're just going to use the standard formula which says that the transfer function g of s equals c into si minus a inverse b into u. So what we want is this expression here, c si minus inverse b. So the first thing and the most difficult thing is to do this si minus a inverse. So si minus a inverse equals s minus 4 minus 3 minus 1 s plus 2 inverse, which if we do that, you'll see we're going to get s plus 2 and 3, 1 and s minus 4, all divided by s squared minus 2s minus 11. So that's the first bit, getting the si minus a inverse. So the next step is to multiply by c and b. So c si minus a inverse b is going to be, the c term is 1 and 6. We'll redo this matrix. So we had in the matrix s plus 2 and 3, 1 and s minus 4, and the b term was 8 and minus 1, and that's all over s squared minus 2s minus 11. And if you multiply this out, it is a bit tedious, so we'll do it 2 steps at a time. So first of all, if you do the C matrix times this square matrix, you get s plus 8, and then 6s minus 21 into 8 and minus 1. And I'll not bother writing the denominator again. And if you multiply that out, you end up with 2s plus 85 over the denominator. So it's slightly tedious. You wouldn't really want to do these things by hand in general. But we've done one here just for completeness. Final question then. Find a transfer function equivalent for the following state space model. Now, in this particular case, what you've been done is you've been given the problem in a control canonical form. So the hope is that you will recognize that the coefficients on the bottom row correspond to the coefficients of the denominator, and the coefficients in C correspond to the coefficients in the numerator. So what I can write by inspection is that G equals, and if we do the denominator first, the highest power comes from here and the lowest power comes from the left. So what you can see is fourth order, so we're going to have an s to the 4. So we get s to the 4 minus 2s cubed minus 4s squared. There's no s term, and then plus 1. So that's just reading those coefficients off the bottom row. And then in a similar way, the highest power comes from the right hand side on this C. So we're going to have 5s cubed plus 2s squared minus 3s plus 1. So if you know your control canonical forms, you get to a point where you can just write this down by inspection. Now, this question here is one which would be somewhat tedious if you got this in a paper and pen exam. So you're given a state space model, and you're given a transformation, and you're asked to find the matrices in the transform space. Now you'll remember that the definitions of the transformation required are A hat is given here, TA T inverse, B hat is TB, and C hat is C T inverse. And if you were to do that on pen and paper, you would be well fed up. So what I would suggest instead, if you get a problem like this, go to MATLAB, and here you can see I've gone to MATLAB and I've just entered the matrices. There they go. So we run those, and let's get the command window so you can see it. So enter the matrices and then just do the calculations there on MATLAB and see what you get, because otherwise it's just going to take ages and not get you very far.